Hello, Calculus 2. We're in Chapter 6, looking at a little mini version of differential equations, and we move into 6.2. We look at exponential growth and decay, which is a topic you probably did in algebra sometime before. But check it out. Look how it pops up in differential equations. So we have this English sentence here. It says, the rate at which, and I made this up, the rate at which an amount of stuff, y, changes over time, t, is directly proportional to the amount of stuff present at any time. So I read that to you. It's a sentence. It's an English sentence. And I called it the amount of stuff, but anyway, this is a model. And you can take this sentence and you can write it as a mathematical sentence, and it's a differential equation. Look what it says. Let's write it again. The rate at which an amount of stuff changes over time. The rate at which an amount of stuff changes over time is an instantaneous rate, and it is the derivative, y prime. Or, in fact, let me just write it like this. It's dy dt. The rate at which y changes over time. I want to write it like this, but that's y prime. Here comes a word, is. The rate at which the amount of stuff changes over time is, that's easy, directly proportional to. So it's directly proportional to. So then you introduce a proportionality constant, k. That's a proportionality constant. I'll write that here. Proportionality constant, k, multiplied by, what is it? Wait, directly proportional to the amount of stuff. The amount of stuff is y, present at any time. That's just y as a function of t. So look what we have. We have a differential equation. Here, I'll get rid of that. That was my derivative, y prime. The rate at which the amount of stuff changes over time is directly proportional to the amount of stuff, y. So a classic differential equation, a lot of stuff behaves like this, and we want to solve this differential equation. And I taught you how to separate and integrate. The variables are y and t. K is a constant. I would separate. I'd multiply the dt over here. But that means I want the y over here with the dy, so I would divide by y. So here we get a dy over y equals k dt. So that was separating the variables, t and y. And then I integrate this side with respect to y. I integrate this side with respect to t. I integrate both sides. Separation of variables. When you integrate this side, of course, you get the natural log of y, and perhaps I should put absolute value of y on there. And when I integrate this side, I get the kt plus c. We did a problem similar to this, I think, but here, this is classic. Now, I do want to solve for y. I want to solve for y and make it an explicit solution. I mean, in a way, we solve the dE. We have what's sitting here as an implicit solution. But I want to solve for y, so I'll e both sides. E both sides. And let me just say, when you e both sides, you don't e each term. You e the entire side. I might have said that before. The e and the log cancel. We get y. And I drop the absolute value because, why do I do that? Well, e to the anything is going to be positive. So this result is positive. E to the anything is going to be positive. This result y is going to always be positive. So I don't need absolute value. And then on this side, I do this cool move. Watch this. I'd like you to understand this. This is e to the kt plus c, which is e to the kt times e to the c. Because that's when you multiply these bases, you add those exponents. So I'm doing that in reverse. I have these added exponents, so I write it as multiplied bases. That e to the c that c is an arbitrary constant. That e to the c is just as arbitrary, so I kind of absorb it and I call that c. So my result is this, y equals, I'm moving up here, y equals, this is a c times e to the kt. And that's it. That's your classic model for exponential growth an exponential decay. When k is positive, we have an exponential growth curve. It kind of looks like this. When we have k is negative, we have an exponential decaying curve that kind of looks like this. And this model works for a lot of things in nature, in life, behave like this. Sometimes we have to modify this model, and we'll look at something like that a little later. But anyway, a lot of things act like this. I kind of generically call this an amount of stuff. But first of all, populations can grow exponentially. Populations of countries, of populations of bacteria, populations of animals, nature, populations can grow exponentially because the rate at which they grow is directly proportional to how many are there. Money, earning interest in the bank, can grow exponentially. The rate at which it grows is directly proportional to how much is there. Money, earning interest, compounding interest can grow exponentially. Things can decay exponentially. Radioactive substances, the rate at which they change is directly proportional to how much is there. They decay into a different substance, so they decay exponentially. So a lot of things act like this, and so there's a lot of good sort of word problems here. But what happens usually with the word problem is we assume it's going to follow this model, and then we end up working with this model, and the calculus has been done for us. So this model leads to this differential equation. We solve this differential equation in general, and we get this model for exponential growth and decay. So then when we do these word problems, we tend to just grab this and do this, and the calculus has already been done, and it tends to be a good algebra problem is what it is. Let's just try one quick. I'll just make one up. So if I say that I had, let's say, I have 100 grams of carbon-14, and I'm not a chemistry teacher, but I think that's an isotope of carbon. Carbon is normally carbon-12. We're going to use this model. I have 100 grams of carbon-14 in the half-life of carbon-14. The half-life of carbon-14 is 5,715 years. I think there's some different books have some slightly different numbers, but that's true. And what does that mean? The half-life means it takes that many years to lose half this stuff. Remember, this stuff is decaying. What's really happening is the carbon-14 is radioactive, a little unstable. Again, I'm not the chemistry teacher. And the neutron's got a couple, it's an isotope of carbon, it's got a couple extra neutrons in it, and those neutrons shoot off and it decays into carbon-12. So when we say it decays, it decays into something else. It's no longer carbon-14, it's now carbon-12. It stabilizes into a more stable element. So in 5,715 years, half of it will decay. And that's an interesting, we could talk about that. That's a probability number there. But anyway, so here's the question. How many grams are there left in 20,000 years? Now we should use our model and play the game. Just to sort of cheat, you ready? I'm going to sort of cheat here a second. You know, anyway, so one thing you do is you kind of get organized. When t equals 0, how much stuff did we have? That was 100 grams. And we know that in 5,715 years, I'll lose half of it. I'll have 50 grams. So that's a couple of facts I know. That's based on this. Somebody gave me this half-life. Just keep going. If I go another 5,715 years, which would be 11,430 years, that's another 5,715, I think, we would have 25 grams. If I do it again, 5,715, that would be 16, that would be 17,145 years. Y would be 12.5 grams. I said 20,000 years, which is a little bit more, so I'm just going to roughly guess about 10 grams. That's my guess based on this estimating kind of idea. This is not linear depreciation or decay. This is not a line. This is an exponential decaying curve. Every 5,715 years we lose half of the previous amount. So there's not a common slope here. No, there's not. So this is not a line. Anyway, usually what we do is we don't estimate it like that. We use this model, like I said. And so using these two first pieces of data, though, were given in the problem. And I can plug in a 0 into this model for t, and the answer y is 100 grams. But basically that tells me that c is 100. Watch. You plug in 100 for the y, you plug in a 0 for the t, and without knowing k, e to the 0 is a 1, so guess what? You just learned that c is 100. Often in this model, c is known as the initial value. C is known as the initial amount or the initial value. Again, the starting value, the starting amount, the initial value, but that corresponds to t equals 0. I mean, that word initial value means t equals 0. So c is 100. Good. This next piece of information will help me find k. All it needs to be is another piece of information, but in this particular kind of problem, it's called the half-life. And I'm going to erase this and do this again here. What I'm going to say is, in this model, I'm going to plug in 50 grams and 5,715 for t. That piece of data will help me find k. So here we go. I'm plugging in a 50 for the y. I already know the c is 100. The e, I don't know the k, but I'm plugging in 5,715 for the time. And so I can do a little math here and find k. Divide by 100, that's 1/2. Divide by 100, divide by 100, that's 1/2. E to the 5,715k. Take the natural log of both sides. The natural log of 1/2 equals the natural log of the e, cancels it out. You get 507.15k. You divide by that 5,715, and so k is this number. We got this by knowing its natural log of 1/2 divided by 5,715. You might want to just leave it as that number. You can pick up a calculator and decimalize it. I would not round off this number. In exponential growth and decay, the k, I would keep the k, I would keep about 1,000,000 decimals. What is it? The natural log of 1/2 divided by 5,715 is, it's written in scientific notation. I'm going to write it as -0.001212855285596. Wow. And like I said, I would not round that off. Students who round it to 2 or 3 decimals, it throws this off big time. It's exponential growth and decay, and the more you round off that k, the more you round off the final answer. Well, I'm ready to try to find the answer, because what I have now is I have the c, I have the k. In other words, I have the model. Remember, we predicted about 10 grams. Let's go over here. I have the model. I found c, I found k. My model is 100 e to the kt. And when I write this k, I'm going to go ahead and write that. The natural log of 1/2 over 5,715 times t. And now I can answer any question they want. They may give me a time and ask me for the y. They may give me the y and ask me for the time. But this model now, I can answer any question they want. They do ask me to plug in t equals 20,000 years. So again, I need my calculator. That's 100. e to the natural log of a half over 5,715 years times 20,000 years. Be careful how you use your calculator here. It's a shame to do all this math and then screw up your calculator. I've got k sitting right there in my calculator now, so I'm going to times it by 20,000. I'm going to e that number. I am going to multiply by 100, and I get 8.84 grams. That's interesting. I predicted that. Close enough. Cool. I would round the final answer. That's the number of grams. All right, that was fun and kind of easy. It's algebra, a lot of algebra. So good luck with the homework. I might help you with some more problems.